Chapter 23 Test Review. Question 1. We have an air-filled parallel plate capacitor, which means we have no epsilon R. The electric field has a strength E between the plates. The capacitor is disconnected from the source of EMF, and the separation between the plates is doubled. So we have Q equals CV, we have C equals epsilon naught A over D. So the field, of course, is V over D. Now we are going to double this, but we are also going to do work against the field to pull these plates apart, and so we will also double this, and so we will have an answer of B 2V over 2D being E. Question 2 then. A parallel plate capacitor, square plates of length L separated by distance D, is filled with a dielectric. Second capacitor has square plates of length 2L separated by distance 2D and has air as its dielectric. Both capacitors have the same capacitance. So we have capacitance 1 is epsilon naught epsilon R L squared, which is A over D. Capacitance 2 is epsilon naught 4L squared over 4 over 2D. And so we have epsilon naught 2L squared over D. So epsilon naught 2L squared over D equals epsilon naught R L squared over D. Epsilon naught L squared D and D. So epsilon R equals 2. And so the answer is C. The graph shows the variation of PD with charge for a capacitor when it is charging. What statement can be deduced from the graph? Charging current is constant, so that's the rate of supply of charge. The energy stored in the capacitor increases uniformly with time. The capacitance is constant. The power supply used to charge the capacitor had a constant terminal PD. Okay, so the first two of these involve time, and there is no way of judging time from this. So we can't say A or B. It might be true, but we don't have any evidence for that. C, the capacitance of the capacitor, is constant. Well, we know that Q equals CV, so C then is Q over V, which is 1 over the gradient. And the gradient is constant, therefore C is constant, so the answer is C. Question 4. Question 4 is a little bit opaque, I think. A parallel plate capacitor is fully charged and then disconnected from the power supply. A dielectric is then inserted between the plates, which rule correctly identifies the charge on the plates and the electric field strength between the plates. Well, if you have connected your capacitor, charged it, and then disconnected it, there is no way for charge to flow on or off the plates. So it can only be A or D. So the field strength must either increase or decrease. Now, by putting your dielectric in there, either the distance between the plates is not going to change, or the distance between the plates is going to increase. And since your electric field is V over D, it either remains the same and you don't have that option, or the distance increases, so the field strength decreases, and the answer must be D. So there's a bit of deduction involved in that. Question 5 then. Capacitor, capacitance C, charge Q, and then we double the PD. What's the change in the energy stored? Note it says change, not the new energy stored. So energy stored, we're looking at in terms of Q and C, is Q squared over 2C, a half Q squared over C. Now, if V goes to 2V, then Q goes to 2Q, since Q equals CV. So there's energy 1. Energy 2 then would be Q squared would be 4Q1 squared, if you like, over 2C, which is 2Q squared over C. So the difference between that and that is 3 over 2Q squared over C. So the answer is C. Question 6. We have a capacitor, consists of two parallel square plates, side L separated by distance D. So C is epsilon naught L squared over D. There's C1, right? What is the capacitance of a capacitor with a side 2L and D over 2? So C2 then would be epsilon naught 2L squared over D over 2. So that is 4L squared times 2, 8L squared over D times epsilon naught. So it's going to be 8 times the capacitance. The answer is D. Question 7 then. A capacitor of capacitance 120 microfarads is charged and then discharged through a 20k resistor. What fraction of the original charge remains after 4.8 seconds? So our capacitor is 120 microfarads. The resistance is 20 kiloohms. The time is 4.8 seconds. The time constant, CR, is 120 times 10 to the minus 6 times 20 times 10 to the 3. And that is 2.4 seconds, which of course is half of the time we're being asked about. So our charge after one time constant will go to 0.368 of our starting charge, and after a second time constant we go to 0.368 of that. So that is 0.135, and therefore the answer is A. Question 8. Initially a capacitor stores 600 microcoulombs of charge. When it loses half of this charge, the potential difference across it decreases by 50 volts. What is the capacitance? Well, since Q and V are proportional, you could say that 300 times 10 to the minus 6 Q equals C times the change in PD that resulted in that change in charge. This gives you capacitance of 6 microfarads. Now you could also, that's answer C, you could also have done that by saying Q equals CV, and so 600 times 10 to the minus 6 equals C times V, and 300 times 10 to the minus 6 is C times V minus 50, and working it out from there, you get the same answer. Question 9 then. The separation of the plates of an isolated charged parallel plate capacitor is increased. What also increases? Well, the capacitance, no. That doesn't happen. The charge on the plates, well, that's not going to happen, because A doesn't happen, and C isn't going to happen, because actually the electric field strength is inversely proportional to the distance, so the opposite would happen. And you might say, well, the answer has to be D, because it isn't A, B or C, but let's explore the reasons for that. We have a fixed charge on our plates. And the capacitance, of course, is going to fall because we are increasing the distance. Remember that C equals epsilon naught A over D. So if we increase this, we decrease that, which is why A does not increase. Sorry, why the capacitance doesn't increase and why A is wrong. So C falls, therefore V rises, since Q equals CV, of course. Or, of course, you could argue that work is being done against the field in shifting these plates apart. There is an electric field between here, say positive and negative, so they're attracting. By moving the plates further apart, you're doing work against that field, and so you're increasing the potential. Either way, you can do it mathematically or you can do it physically, but that's the answer, D. Question 10. The initial charge stored by a capacitor of capacitance 0.5 microfarads is 2 microcoulombs, sorry. The capacitor is then discharged through a resistor. How much energy is stored by the capacitor after a time equal to 1 time constant? So, the energy stored is a half Q squared over C. We've got Q and C, so that's kind of handy. So stick in our values and we'll get 4 times 10 to the minus 6 joules if we do that. Then after 1 time constant, we're going to fall to 0.368 squared, because of course Q has fallen by 0.368, and so we get 0.54 microjoules, which is B. Question 11. Says a 500 microfarad capacitor is charged to a PD of 10 volts. And then discharged through a 100k resistor. What is the time taken for the PD to fall from 10 to 5 volts? Well, V equals V naught e to the minus t over CR. We have 5 is 10 times e to the minus t over cr, which if you multiply them together is 50. Take our logs of both sides. And you get t to be 35 seconds, which is A. Question 12. Which of the following statements about a parallel plate capacitor is incorrect? The capacitance of the capacitor is the amount of charge stored by the capacitor when the PD across the plates is 1 volt. Well, that is absolutely the definition, so that's true. Uniform electric field exists, yes. The charge stored on the capacitor is inversely proportional to the PD across the plates. Well, if you're not sure, Q equals CV. Is the charge inversely proportional? No, it's not. So that's not true. And that is our answer then. The energy stored is proportional to the square of the PD. Well, you know that. So, question 13. A voltage sensor and a data logger are used to record the discharge of a 10 millifarad capacitor in series with a 500 ohm resistor from an initial PD of 6 volts. The data logger is capable of recording 1000 readings in 10 seconds. After a time equal to the time constant of the discharge circuit, which one of the rows gives the PD and the number of readings made. So let's say we take 1000 readings in 10 seconds. So 500 readings would be 5 seconds. 50 readings would be half a second. So let's take 500 readings, 5 seconds. So we have V equals V naught e to the minus 1. This time constant, of course, 10 times 10 to the minus 3 times 500. So that's 0.368 times 6, which gives us 2.2. So the answer is D. Now you might not have hit on that straight away. You might have chosen to take one of the other figures here, for example, or here, and found that it didn't work. So you'd have tried another one. Question 14. A variable capacitor has a capacitance which can be varied from 6 picofarads to 3 picofarads. The capacitor is set to a maximum capacitance and fully charged using a 48 volt supply. The capacitor is then disconnected from the supply and isolated. Finally, the capacitance is reduced to its minimum value without any charge being lost by the capacitor. Which line correctly shows the PD and the charge? Well, we know the Q is constant. Equal to CV. So C is going to 0.5 C. So if Q is constant, then V must go to twice V. So the charge remains the same. As you work out the charge, you get 2.88 to the minus 10, Q equals CV. So you're looking at one of these three. You're going to double on the PD. The answer is C. Question 15. The capacitor in the circuit is initially uncharged, the switch S is closed at time t equal to 0, which pair of graphs correctly shows how the PD and the current change with time. Well, it's initially uncharged, so it's going to charge, so the PD is going to rise exponentially, and the current, of course, is going to fall, so the answer has to be A. Nothing too complex about that if you know what you're talking about. Question 16. An uncharged 4.7 nanofarad capacitor is connected to a 1.5 volt supply and becomes fully charged. How many electrons are transferred to the negative plate of the capacitor during this charging process? So let's work out the charge and divide by the electronic charge. So Q equals CV. Doing that, you're going to get 7.05 10 to the minus 19. Divide that by the electronic charge, 1.6 times 10 to the minus 19. So that's 9, not 19. Which gives us an answer of C. Question 17. When fully charged, a 2 millifarad capacitor used as a backup for a memory unit has a potential difference of 5 volts across it. The capacitor requires to supply a constant current of 1 microamp and can be used until the PD across it falls by 10%. For how long can the capacitor be used before it must be recharged? Well, Q equals CV gives us 1 times 10 to the minus 2 coulombs. 1% of us, or 10% of that, is 1 times 10 to the minus 3 coulombs. So if we say this much charge is going to leave the capacitor at this rate. If we divide our 1 times 10 to the minus 3 coulombs by our 1 times 10 to the minus 6 coulombs per second, then we get 1,000 seconds, which is D. Question 18. When the capacitor is fully charged, which one of the following statements is incorrect? Well, let's look at the energy stored. A half CV squared. If you do that, you get 2 millijoules. So that's right. Total energy taken from the battery during the charging process is 2 millijoules. Well, that is not true, is it? That's our wrong one. But the PD across the capacitor when fully charged will be 20 volts. PD across the resistor will be 0 volts because there is no current. So the answer is B. Question 19. Initially, a charged capacitor stores 1600 microjoules of energy. When the PD decreases by 2 volts, the energy stored becomes 400 microjoules. And the question is, what is the capacitance? Now, I would say the way to go about this is E equals a half CV squared. E is going to a quarter of E. So V is falling to half of its original value. So we know a drop of 2 volts is a drop of 50%, and so V is 4 volts. So you can then work out the capacitance. 1600 times 10 to the minus 6 equals a half by C by 4 squared, which is 16, gives you C to be 200 microfarads. Now you might be tempted to try and do this on some kind of proportionate basis, and saying delta E is a half C delta V squared, but that's not actually true, because since E is a half CV squared, then what you're saying is that second energy is a half C V minus 2 squared, and clearly the change in the energy here is not equal to, if you multiply out that, the change in the energy is not equal to a half C delta V squared. So make sure you don't do that. You're given nice simple ratios here for a reason. Question 20. Switch S in the circuit is held in position 1, so the capacitor becomes fully charged to a PdV and stores energy E. The switch is then moved quickly to position 2, allowing C to discharge through the fixed resistor. It takes 36 milliseconds for the PD across C to fall to V over 2. What period of time must elapse after the switch has moved to position 2 before the energy stored has fallen to E over 16? So, E is of course a half CV squared. You'll get E over 16 when you have V over 4, which of course is 2 times 36 milliseconds, because it falls by half and then falls by half again. That is to say, a half over half, because that is the definition of exponential. And so the answer is B. 21. The nuclear fusion device requires to deliver at least 1 megajoule using capacitors. If the largest workable potential difference is 10,000 volts, what's the minimum capacitance of the capacitors that should be used? Well, we want 1 megajoule, and we want a half CV squared, which is 10 to the 4 squared, gives us C to be 0.02 farads, which is B. 22. Which line A to D in the table gives the correct pair of graphs showing how the charge on the capacitor and the current in the circuit change after S is closed? Well, you would expect the charge to rise to a maximum. You'd expect the current to fall exponentially, whether it is charging or discharging, and so on that basis the answer is D. '23. The voltage across the capacitor falls from 10 to 5 volts in 48 milliseconds as it discharges. What's the time constant? Well, let's do the equation. V equals V naught e to the minus t over CR. V over V naught is e to the minus t over CR. V over V naught then, of course, is a half e to the minus t, which we said was 48 times 10 to the minus 3 over CR. Do your logs, out drops CR, 69 milliseconds C. (24) Initially uncharged capacitor of capacitance 20 microfarads is charged by a constant current of 80 microamps, which line A to D in the table gives the potential difference across on the energy stored in the capacitor after 50 seconds. E, of course, is a half Q squared over C. Stick in our numbers. A half times 80 times 10 to the minus 6 times 50 squared over 2 times 10 to the minus 5. And if you crunch those numbers, V being Q over C, you get 200 volts, which is D. And finally, question 25. The graph shows the charge stored in a capacitor as the voltage across it is varied. The energy stored in microjoules when the PD across the capacitor is 5 volts is, well, it's A. Hopefully you're happy with that. E is a half CV squared.